So let's take a look at the forces that hold molecules together when they're in the solid and the liquid state. What is there that's keeping this in this solid arrangement? Something's holding it together, otherwise everything flies apart and becomes a gas. In ionic compounds, we know what that is. This plus minus, opposite charged ions are attracted to each other. So this force here is called an ionic bond. Ionic bonds are very strong. All ionic compounds are solids at room temperature. It takes a lot of heat to get these things moving fast enough in vibration to where they can break that ionic bond and roam around as a liquid, hundreds of degrees centigrade. But if these are charged ions, so we can see that attraction of opposite charges holding them together. What about if they are molecular compounds? What is holding them together? If they're molecular compounds, they are not charged. They're covalently bonded together, and they have not exchanged electrons. They're sharing electrons. They are not charged. What's holding them together when they're in the solid and the liquid state? Something's got to be there, otherwise they'd be flying apart. So when I'm looking at covalently bonded molecules that are sharing electrons, they have not exchanged electrons or given or taken electrons. They're sharing electrons. But we saw that some of these compounds are polar, meaning one side of the molecule has one of these big electron polars, one of these more electronegative atoms, meaning they're pulling electrons towards them. So if I've got one of these guys, the big 4 electron polars on one side of the molecule, one side is more electron dense. So that it's a neutral molecule, but the electrons are just not evenly distributed. They're over on this side where these guys are. If that's electron dense and I have this and it's got a neighboring molecule near it, one of its neighbors, same molecule, it will rotate, opposite charges attract. The negative side of this will be attracted to the positive side of this one. That's an attractive force. That is going to tend to pull them together. And we would see the same thing all around. So there is this attraction of the electron dense area of one molecule attracted to the part that's less electron dense of the other one. That is a attractive force between them. We call it a dipole attraction. Why dipole? It has to do with this. In a polar molecule, the degree of polarity or the amount of polarity we call the dipole moment. It's a measure. How polar is it? Is it a little bit polar? Is it a lot polar? That's called the dipole moment. Hence we call this attraction the dipole attraction. The attraction depends on how polar is the molecule. Let's look at an example. If we look at this molecule, it's called dimethyl ether, but it's got carbon with an oxygen bond in between the 2 carbons. I've got that 4 domains around the oxygen. What does that do? That gives it a bent shape around the oxygen. And so what have I got? There I have oxygen, one of the big electron pullers, electronegative atom, on towards one side. It is just a little bit off of the center, so it looks linear if I do it this way, but we know that that's bent. And so the oxygen is just a little bit on one side, so this molecule we would say is slightly polar. There's enough holding it together, the boiling point equals negative 11 degrees C. So there's enough holding it together that I got to get this up to a negative 11 degrees C, and it can be a liquid. So the negative side of one molecule is going to be attracted to the positive side of another And there's my dipole-dipole attraction between dimethyl ether. Now this dipole-dipole attraction, as we mentioned, depends on how polar is the molecule. Let's look at another one. This one is acetone. In this one, in this molecule, I've got the center carbon, and the oxygen is bonded off of the center carbon with a double bond. 1, 2, 3 domains. And that gives me my trigonal planar arrangement. So instead of the first one, which is just a little bit polar, this one, that oxygen is sticking way out there. So it's much more separated from the center, definitely pushed way out to one side. A big electron dense area out this side, and it's extended out, so it's more polar. Slightly polar here, more polar, we would expect greater dipole-dipole attraction, and it is the boiling point. (56°C). So now I got to get it, acetone is a liquid at room temperature, I got to get it above 56°C in order for me to break those stronger dipole-dipole attractions, because I got a more polar molecule. So a little bit off, slightly polar, I can get some dipole-dipole attraction, but if I get a more polar molecule, the dipole-dipole attraction becomes stronger, which means I got to get it up to a higher temperature for it to overcome those attractions and become a gas. And then let's look at another example of a similar molecule with a slightly different type of intermolecular attraction. So here's a very similar, compare these two molecules, 3 carbons connected. In this case, the oxygen's off of here. Here I got the oxygen off to the side, but importantly, there's a hydrogen bonded to this oxygen. Here there's no hydrogen bonded. What does that do? If I have one of my big electronegative atoms bonded to hydrogen, NH, OH, FH. If I have this situation, not just one of these big 3 electronegative atoms, but specifically bonded to a hydrogen, what makes the big difference there? Hydrogen has no core electrons. It only has 1 electron. It's sharing its only electron. That electron is being pulled towards the big electron polar oxygen. So therefore, since there's no core electrons there, that represents an exposed proton. The bonding in this situation is called hydrogen bonding. And that is even stronger than dipole-dipole. 2 very similar molecules in a lot of ways. This one has the OH bond, that one has oxygen, but these H's are bonded to not very electronegative carbon. So it doesn't have the OH bond. Look at the difference in boiling point, 56 degrees up to 97, stronger attraction. Hydrogen bonding is stronger than dipole-dipole. It's like a special case of dipole-dipole, where that exposed proton that's bonded to this, these electronegative atoms becomes a big factor, right? So that becomes even a stronger attraction between the opposite charge. The positive exposed proton here will be attracted to a neighboring molecule to the negative side of this neighboring molecule. So we will next look at, in the next video, we'll look at what about if it's a nonpolar molecule. We've seen how polar molecules can be attracted. Is there some attractive force that is holding, even if it's a nonpolar molecule? And there is.